Okay, ready? We start another project. As I told you, this class is the same class. Just present you all the applications. Only to let you know, this procedure is not that important. Okay? There are a variety of applications. And depending on your expertise and interest, you could have different applications. Let me show you one of my projects. And this should be still work. Let's be using Baltimore. Okay? Here's Baltimore. In case some of you has not been in Baltimore yet, they want to DC. If you get a chance to stop by Washington, D.C., take about 1 hour from Washington, D.C. to Baltimore. Washington, D.C. does not belong to any state. It's contact from Maryland, from Virginia together, become a Washington district, kind of special district. Baltimore is the major city, the largest city in Maryland. Baltimore belongs to Maryland. But this is a corridor. Baltimore and Washington, D.C. have a 4 route, so it's a major harbor in the East Coast. Okay, so this is a more recent project from my group, work on so-called multi-modal emergency evacuation system. And as I mentioned to you yesterday, we talk about evacuation, but actually we use all the money for transportation purpose. Evacuation is the time you really need a very good transportation and logistics system, okay? So here I show you a typical evacuation process. I hope to share with you what are the problem natures and what are the issues, where can you do study, and where you have learned from the class have the opportunity to apply here. That's the whole purpose of these projects. First, by some source of detection by the security Homeland Agency, they will inform the city or state or whoever got the phone call from 911 will activate evacuation. So they were announced by all kind of medias and let you know when we start evacuation. And then second, they have to identify where are the impact zones, right? In Baltimore, it's in the harbor. Baltimore, the central part of metropolitan is a harbor. So once you have emergency, then next, how far the impact going to be? So all those people within the impact zone need to be evacuated. And the first step, you can use Taipei as an example. If something happened in Taipei downtown area, you need to evacuate. The first one will be what? Evacuate those people have to walk. Walk to where? Walk to either subway station or parking garage. Evacuate the pedestrian first. And then all the pedestrian will be converted into what? Car unit or subway unit, okay? In the Baltimore case, we actually include subway, but Baltimore only have one subway line, unlike DC have 6 or 7 subway lines. So we treat that one as separate study. So once you evacuate pedestrian, then all the, we say, mobilize evacuation with passenger car and transit systems. You have to use a mass transit system or carpool designed to evacuate a large population during a time window. A time window is a window you have to evacuate, otherwise you will die or seriously injured. And then once the passenger car has been identified and assigned the route, and then you have to guide them to evacuate in order to safely, efficiently move out the control boundary. Okay, there's control boundary. So in those cases, here's a model input, identify impact zone. That will not be transportation project. That is determined by the Homeland Security and the we call first responders. They will tell you, okay, currently with the maybe the dirty bomb or chemical attack or any biological attack, then the impact area will be different depending on the weather condition. Okay, so this is model input. Second, the impact zone will based on the model input to identify the impact zone. The impact zone in the later project will show you actually impact zone could be changing over time. If the weather, the wind direction is in favor to evacuation, the impact zone could be increasing over time. Okay. And then assigned. So the transportation problem here is during the evacuation, think about Taipei City. When you try to evacuate, then what happens? You have two types of transportation mode. One is pedestrian walking on the street and try to find somewhere to evacuate, to escape from the disaster. And second type will be cars moving, right? So here's a mixed flow problem in the network. You have pedestrian walking on the network. You have buses on the network. You also have some people already have access to cars. They are moving on the network. So the network is different from the typical network. It's a mixed flow congested network. Mostly pedestrian will not play a major role in most urban transportation problem. But during the evacuation, in a short time period, you want to evacuate people. So pedestrian become a major transportation mode in the process. So here's a mixed traffic flow problem. And then after everybody get on the bus, get on the car, then from Taipei City want to move to other city, then become what? Single modal problem, because no one going to walk to evacuate. Then you volunteer to die. Okay, so after some time period, you already load everyone in the car or bus system. Then the model, the problem become a single mode network problem. So this evacuation typically for large city include two stages. Okay, first in downtown area, we think the impact zone. Impact zone means directly polluted or damaged by some kind of attack, okay, or by natural disaster. For example, Kaohsiung's that explosion is counted as one of the natural disaster. It should have some type of evacuation. Maybe not in large scale, but still, it could be worse. No? If continue a serious explosion, could be a big problem. Okay, so that will be an identified impact zone area and quickly evacuate all people within the impact zone to a proper area. As I saw from the newspaper, some people die in the process of trying to escape from those areas. Those are examples of without well-designed evacuation process. And then after people move out the evacuation zone, then it could be within the city, then you try to completely evacuate the city. You still have the transporting work, which will be mainly passenger car or the buses, okay, without pedestrians. So these are the two processes. This process represents this part, covered the major direct impact area, and this side is what? Indirect impact area. And those are the control points. Means you want, in the evacuation, you don't want everybody to do their own way, find their own path. Then it will be a big disaster and congestion bottleneck too. You want all the traffic to follow you, follow your guidance, go to those so-called control points, and you give them the direction where you should go and control the departure patterns. Okay, those are the called orderly way of stage evacuations. Okay, then I will show you non-mathematically where are the key issues, a key component you should cover in doing the research in this area. Okay, this actual Baltimore case. One of the major issues is downtown Baltimore. This area is a football stadium. Have a lot of people evacuate from here. A lot of people here. So this here close to the harbor. Okay, so something happened, you have to evacuate those people, or even nothing happened after football game. Football game, the stadium could accommodate close to 200,000 people. So 200,000 people, if they lost the football game, then 200,000 people could be a traffic problem. Okay, they were so mad. Then they were slow on the street, complain, smash something. If last year, the Raven, the football team, won the national title. What's the problem too? Because everybody's so happy and create a problem there. So we always have in the summer now, in this fall season now, every weekend they have to deal with the evacuation problem. Of course, the evacuation windows will be a little more flexible rather than actual emergency, but still a big traffic problem. Okay, so our challenge that time is, okay, we use this example, compare with police evacuation plan with our own plan, see whether we really provide a better plan for them or not. Okay, so Baltimore downtown is the harbor. This stadium all in the downtown area. If you know the Baltimore, you found out this entire city is developed along the downtown in the harbor. It's a nice place to go. Okay. So the first part of your model, different from the traditional model. First part, most people will be where? Inside the building. Okay, unless it's at night. That's different. They will be on the street. So there is another area of research, how to evacuate people in a high-rise building. Okay, so if you study in a fire protection area, let's say Taipei 101, if something happened, how are you going to evacuate those people in 101, so high-rise building? That is a serious research problem. It's a lot of study, not in transportation, but it's a serious study. A major metropolitan, you have high-rise building. How are you going to evacuate the people? Those are very critical. 1 minute, 2 minutes differences, then you could cause a lot of people to die. Okay. So here we don't deal with this part. We assume those people should be able to, based on some plan, get onto the ground, and then it's our job. Once they get on the ground, first you got to let pedestrians know where they should go. Think about if now people tell you, okay, we're going to evacuate from the campus. Do you know where to go? Everybody will run together, right? So based on Japan and several South America's example, a disaster experience, half the people die is not by the disaster, it's by what? Killing each other, trapping each other, create accident in the process, because everybody is eager to get out at the cost of other people's life sometimes. Okay, so it's very important to, in those cases, recently start to intensify again. After 9/11, it was a very important issue, and then for a while they kind of slow down the process, less pressure. Now somehow something happened. If you go to the United States now, you found out airline checking you every step. Okay, so now intensify again. During that period, our purpose, our strategy is
you give every major building people where are the assembly location they should go. Or in some area they use a zip code. You know. If your zip code, you know, post office zip code, you inform you your zip code in which area, you should go to which location. And now it's much easier. You have a cell phone, so we can send a warning sign, remind everybody it's going to have a evacuation by when. If your building located in which zip code, you should go which location to wait for help. Okay. Because in the short-term windows evacuation, we may not allow you to go to a parking garage to pick up your car. Okay, it may take too long or block other people's. So the first step is to send those people go to those locations. Some will be a parking garage. In metropolitan area, many people do not have a car, do not have access to cars. So you also have to allocate them to bus stop or subway stop. Here we do not include subway because in Baltimore only have one subway. Okay, we take as same as bus mode. So the pedestrian flow, you need design for them. Okay, without guidance, pedestrian will go everywhere. Okay, so then those intersections, as I mentioned yesterday, you will experience what? Large volume of pedestrians. So here your signal cannot use the standard signal. Standard signal, what do you think about? I need to go to escape, to survive. And signal is red face. Am I going to wait? I don't think so. Also in the early stage of the evacuation, network will be what? Mostly pedestrians. And second stage will be what? Mostly passenger car, because you already get onto the passenger car. So the two different natures you have to take into account in modeling process. Okay, so first you can see here you have it from transportation point of view, you need to have one pedestrian assignment model. When you assign, you need to know each location's capacity. You don't assign all people to one bus station, but then the waiting line is too long, okay? So there's traffic assignment problem, pedestrian assignment, and vehicle assignment, okay? And pedestrian go into a parking garage will become what? Become a cars come out, right? You have pedestrian flow go into a parking garage. And if you go to parking garage, suppose you have a car or carpool there. So you have a model have to take into account the multiple commodity issues. Pedestrian go in and come out with passenger car. Okay. So the nature of the problem is different from the simple mode assignment. And you also need to have a spatial signal design for those critical intersections. Okay. So the entire arteria in those cases will be what? A mixed flow problem. Okay. So we design a spatial simulation model to deal with simulate pedestrian and the vehicle together, called mixed flow simulation. It has been published in the simulation journals. So here, hopefully you can recognize where are the real issues, okay? If your research do not grounded on real world issue, then your research can only be publication, okay? Can never be useful. So here just indicate mixed flow intersections. You have to provide spatial phases for the pedestrians. Otherwise, pedestrians not going to follow your signals. And then you have the guided bus route. So here bus route different. Here, in this case, we use a school bus to pick up the pedestrians. In United States, you know, every high school from elementary to high school, you always can take a school bus. You always have a school bus. Of course, your parents, you want to give you a ride, it's okay. Otherwise, every family is entitled to have a school bus. So we have a lot of school bus. So in this case, we use a school bus and some in-route bus. Some bus or in US, bus is not very popular, okay? So the bus, in terms of the fleet size, may not be sufficient. So we have to use together with the school buses. So in this case, bus will be assigned to pick up a point, okay, and to pick a bus. I will show you later in the models, okay. The paper, in this case we published 4 papers. This one student dissertation and 2 programmers work together. We published 4 journal papers and 3 DRB papers in this area. We will show each issue to you. Okay, so this overall system structures. So show you where are the model. One, you have mixed flow model I just mentioned to you, okay. You need a pedestrian model. Pedestrian study, although there are some study, but usually most of study is location specific, are not sufficiently general to be applied in different cities. So if you can deal with Taiwan's own issue, you need to have your own study of Taiwan pedestrians, behavior patterns. And second, you have evacuation signal models. Signal model I told you is different. You need to have a pedestrian faces, okay? And bus routing model, because you want the bus come here to pick up those evacuees waiting at stations. And how a bus come? Will bus come pick up everybody at different station, or bus only come to one station and pick all the pedestrians and go and come, okay? So bus route is also different from the typical bus route. It's not a multiple stop. And then once all the vehicles are ready to get out of the city at those boundary control points, then you have multiple locations for your evacuation destination. Then you have assigned those vehicles to those destinations. In this case, this assignment problem is what? One origin to multiple destinations, okay? Different from the typical multiple origins, multiple destinations issue. Okay, instead of showing you equation, I show you the system. You see the system, you should understand what are the models behind, okay? So nowadays, if you want to be a good system engineer doing the transportation, you also need to know the computer very well. You may not know how to program very well, but you need to know how to direct programmer to do the work. Here's actual Baltimore area, okay? And this is our software. See the entire Baltimore region. It's very similar to Washington, D.C. We all has a beltway. Here's the inner harbor, and here always goes to the Atlantic Ocean, okay? And this is a downtown, the most population in this area. If you go to sightseeing, usually it's around this area for sightseeing, and there's a huge beltway. If you get our evacuation targets, let every people get out of the beltway as our own control boundary. Beltway is a control boundary, okay? But destination is a little bit far away. You can see if you need to have such a system. I used to think I was trying to push Taiwan to have such evacuation system for the Taipei and Taichung or Kaohsiung major city. But now I give up, okay? Now I see the government cannot do anything. I don't have hope to waste my time, but hopefully you guys share the idea. It's application of transportation's work. Even you don't have an evacuation emergency, you still can use the system for your day-to-day major transportation event or major activities taking place in the city. So here's our purpose actually deal with the terrorist attack, okay? So actually here I have a list of the potential attack, bomb attack, hurricane attack. Those are given by the government, Homeland Security. Here's time window, evacuation from when to when, okay? Here's of course the function. This is the sequence of operation for the program. As I mentioned to you, when you convert your research into a product, you have to make sure your product is easy to use. Otherwise, government will not use you. They will still call you every day, or they don't use at all. So our job at this stage, especially you work on the ITs, you cannot just finish a paper and equation and models. You also need to go one more step, convert your research. It may not be your own paper. You may combine two or team members' paper together, become a product, and that product have to be designed in a way user-friendly and no need for instruction. This is our process to show how to identify and use a system. Step one, got to identify what type of incident, right? Okay, here's a list. Different type of incident, your evacuation time window is different. Most important is time window, okay? Time window is the key issue. Means within that window, you have to get everybody out of the impact zone. Otherwise, they would be die or serious injuries in their life, okay? Okay, so the impact zone is based on the given information. So from the impact zone, you can identify how many people within this control boundary, within this direct impact zone, okay? And those are indirect evacuation zone. Where do you have those information? Suppose you have a traffic zone in the urban state, in all the urban planning, and every city government, I don't know about Taiwan, but every city or government should have those information. Traffic zone and how many people is resident, how many are working population, people come to work there, okay? So evacuation also related to time. If your evacuation happened at 9, then most of those people will be what? Resident, right? That happened in Washington, D.C. too. If the evacuation taking place at the daytime, then you need to have what? Account for both resident and people working there, okay? So the actual evacuation population could be double or could be triples, depending on the area have a lot of high-rise building or not. Okay, so we have those information. That's information pre-stored in the computer system. So you know how many people in each zone, okay? How many people working there, how many pedestrians, how many cars, okay? For example, you can click in and identify each zone. Okay, see totally how many pedestrians there, okay? That's one. TAZ means a traffic analysis zone for our transportation study. Okay. The reason we allow you to change is what? I told you different time of day, different seasons could be different. The one yesterday I presented Ocean City, in the summer, every zone has a huge population. Weekend and weekday are different, and the winter will be different. So you have a pre-stored database, but you also allowed user to input and make changes necessary. This is a time bar when you try to actually start evacuation, okay? And here show you how many vehicles in those areas, okay? Of course, this cannot be a precise number, but you should have an approximate number. Why? In the downtown area, based on how many parking garage in those areas, how many roadside parking, how many family parking, private parking lot. So you can estimate approximately or maximum how many vehicles could be in that zone. And that is very important because all those vehicles we have to use, mobilize in the evacuation process. And here to show you within the control boundary, where are the, how many bus routes? This one is subway, if I remember, yeah, different color. How many buses are within this control impact zone? Where are the bus stops? Okay, and those information have to pass through all the potential evacuees in this area. Okay, if you work in Baltimore, you will get all those information. You may ask why we want to know the information. Because during the evacuation, if you tell people, oh, you go to which destination, which intersection, they may not all know that well, okay? So the best way is you direct them to the location they typically use or they are familiar with. And bus stop, we believe, is the one most commonly used by the people, okay? Bus stop, they usually know because they take a bus, okay? And bus stop is also located in the area in general more much easier to access by the most people. So we use bus stop as the pickup locations. Certainly you have to study each bus stop may have their capacity, how many people they can stand in the queue there, okay? Otherwise, too many people there, they may block the street and become a bottleneck for the evacuation. So I'm showing you step by step to see, train you to understand the nature of problem, and you can zero in which area you can do a study. Okay, they still have a lot of paperwork on this evacuation area, because that is what is the most important application of transportation research, and it's an integrated application for all kinds of transportation issues, behavior issue, signal design issue, bus route issue, traffic assignment issue. Okay. Here show you every stop, what would be capacity. Okay, you can know whether there are additional room for accommodate more people or not. Okay, so you after clearly understand how many people within the impact zone area, then you start to evacuate these people. Okay. Here's the actual stadium. Okay, here's right in the downtown area. Then you can, from the stadium, you can see surrounding area, where are the potential parking place, and where are the area could people temporarily get together there waiting for the help. So step one, we're going to assign the pedestrian path and pedestrian flow. Here's just an example to show you. Those are parking area, they have a car there, bus stop. So you have to provide a route to guide the pedestrian. As I mentioned to you, you don't provide a route, pedestrian will be what? They will walk to all the different directions, and every possible directions they will go because they are in panic. There are some behavior study on people's response under panic condition. Okay, in some emergency, they lost the direction. They will follow everybody. The area more people to go, and they will everybody follow each others blindly. Okay, so most likely they're going to cause more trouble to everybody. Okay, so you need to give a direction clearly from your design based on the identified capacity and identified demand. So you need a pedestrian assignment model here. Okay, assignment model, you have to think about some may follow you, some may not follow you, and what kind of message, how to give a message to those evacuees to ensure most of them will follow your direction. Those are the research area that you have to worry about, the pedestrian assignment models. So this is one example. We found out how many people from here should assign, 550 should assign to the bus stop. How many people they have a car in the parking garage, okay, and for that bus stop or that parking garage, okay, with different paths. This is actual case, okay. This we use the football stadium evacuation as an example. And second step is this zoom in the network area. Once you assign the route, assign the path, you have to change your signal timing. Okay, you found out that many cities does not have the function to change the signal timing during some special event or incident, or even during the construction zone area. So even the green times waste and cause unnecessary queue. In this case too, you want to do evacuation based on you assign the path flow. The demand different, so you have to change the signal timing to facilitate those people moving around. Otherwise, they want to move, follow your directions. I found out the signal is not moving, and they are going to change to different directions. So again, your system can rule in to find out, okay, what are the current signal design and how should you provide information. For example, here 0.7%, this intersections 70% should go this way, 30% go this way. Okay, so you have to provide your timing plan according to your assigned path flow. Okay, those two. So signal timing has to be continually change. Remember, there are two stages. In the early stage, signal timing have to what? Favor pedestrians, because that time most are pedestrian. But second stage, after most people got into the bus, most people got into the parking garage car, then the pedestrian flow will be converted into what? Vehicle flow. That time, your design signal have to change to favor what? Vehicle rather than pedestrian. Okay. So this we have a spatial model will be designed to accommodate pedestrian. We call spatial mixed flow signal models. Give an example here. You can show this three direction we don't want car to go. We only give the direction to pedestrians. Okay, this coming out of the mixed flow signal the optimization models, part one. Okay, and here's the phase can change. Of course, you always allow the operator to change those plans, because same as in Taiwan or most developing country, Baltimore, Washington D.C., they do have important guys working in some area, so they needed to have special route. Let those guys evacuate first. Okay, especially in Washington D.C. We have my next one will show you Washington D.C. Washington D.C. we design a lot of routes. Finally, have to change a lot, because first they have a special route. President will be taking the helicopter to escape. Okay, but those Congress, senator or House representative, they have their special route. And when they are doing evacuation, those are protected for them. Nobody can use. Okay, so you have taken away those routes. You have to give them special signal to evacuate first, and then at second level, general population can evacuate. So you are doing the design, you don't know, but you allow them to deactivate some route, even you consider optimized. Okay, or this area maybe government that's mentioned, or government's office, and those areas they have spatial functions to let them go first. Unfortunately, these are the case. Okay. Okay. Then once you have a plan, in model, this is a planning model. Okay, this is a planning model, not a real-time operation model. But so you plan to see, based on model, do all the assignment. But in the real operations, you based on your pre-planned strategy to assign. But in the meantime, you want to do an evaluation, use a simulation, concurrently simulate what would happen if everybody follow your pre-planned evacuation. Understand? Most evacuation, there are some percentage of people will not follow you. It's impossible to be ideal condition, okay? But you want to know ideal condition, what would be a time window? If ideal condition, your time window is still too long, then of course in actual evacuation will be much longer. So here to show you, after we do all the assignment, then guidance, then we simulate, see what would happen in the traffic condition. So you can see the initial condition, after how long the evacuation is taking place, what is the pedestrian network conditions. So you can see after this time period, then pedestrian everywhere, okay? So this allows us to evaluate whether our strategy can work or not. And then you also want to see within the impact zone, what would be the vehicle network. You have two overlay network. One's pedestrians, one's the passenger cars. So this part is belong to simulation. Again, you can see this is not a typical simulation. It's a mixed flow simulation. You need to, a network include the vehicles and pedestrians, okay? Most of the simulation cannot do so. This is spatial design and simulation. So you can see this within the impact zone. Okay, this simulation time, over time, what happened in the condition. So you can see getting congested at what time. Then you can see after how long they all will be evacuated out of the impact zone. Another important area you have to check is If we all evacuate in the zone, where they should go? In the boundary of the evacuation impact zone, we set a control point. Because those control points will be, you have police cars stand there. We have police, we call law enforcement people there. Evacuation, you need a law enforcement. But you will not have enough law enforcement to stand at every exit. So usually identify most critical exit point. Then law enforcement will be activate the system and control the process there. So you send all the vehicles, pedestrians go to the control point. So you based on the control point, when they can arrive at the control point, you can see what is a departure pattern from the impact zone and how long would approximately clear the entire impact area. And from the arrival pattern, you can also see whether your plan successful or not. So in doing the operation, you also have to, based on your plan and simulation result and actual condition, to check every control point. What is the arrival pattern of pedestrians, okay, passenger car. In this case, all convert into the car, okay. Within the area, have pedestrian out of the control area. Everyone's supposed to be in the passenger car or buses. Okay, so you have a time-dependent arrival pattern here. Based on arrival pattern here, then you assign the route for them to get out. Some people may ask, why do I need a control point? As I mentioned earlier, evacuation need to be under control. Okay, if you let them go as naturally as their preference, then it will be a chaos. Okay. They use an experiment, they put all the ant in a big bowl and create some fire. I see how the ant try to escape from a couple of small holes. Then you found out without guidance, all the ants will be what? Compact together and crush each other's. Okay. Same as in people's evacuation too. Okay. So you need to have control point, clear guidance, and strong message. Ask them to follow you. I put them in an orderly way to get through the evacuation process. And in the meantime, in the evacuation process, you have to continue to check at different time of the evacuation how many people remain in the impact zones. Why do I say so? Because in real world case, even in your modern case, we are not able to take into account all the complex interaction in this entire impact zone. There are always some of the path, some of the route, some of the intersections you may not model properly or may have been changed. So in the actual evacuation, you found out if you don't do simulation and don't do evaluation and don't constantly check, you may find that most zone people already evacuated, and there's one or two zones people stuck there. That's happened because your network structure may be convenient for some people in some zone to evacuate, but some people in particular zone may all blocked by other people. Okay, or models, mathematical model can never fully take into account all the real world constraints. So we have to be humble to recognize fact. So either in the planning or in the actual operation, you always have to constantly monitor. Do you forget some people in the same area, or some people in some area are blocked by other major arterial traffic flow or not? That's the reason you have to check. Okay, so very commonly one or two zones could be blocked by others. For example, in the first case we found out this zone people are blocked. Most of those has been evacuated. And this because we found out there's two major routes there, and two major routes, the signal time facing was not assigned equally, properly. So a lot of people here blocked by the evacuation. Most people gone there still happen there, okay? That's happening in actual evacuation too, okay? You see emergency, some people just forgot by the whole process, okay? And then we go back to check and convert some of the left-hand phase and left-hand lane into the evacuation route, so make the problem solve. We found it in the DC's case too. Almost every big metropolitan, your mathematical model may ignore some important zone area, okay? So that's the reason you have to constantly check over time what are the status of the evacuation, how many people remain in the evacuation zone, okay? Same as pedestrian. Pedestrian usually less likely to be trapped because pedestrian is more flexible. They don't need to walk on the route, they can walk on the pedestrian ways. So less likely pedestrian zone will be one or two isolatedly ignored by the evacuation process. I see over time, up to what times, mostly are green now or yellow now, represent they all are in good shape, okay? Okay, then not done yet. You just see they already go to the bus stop or the pre-assigned loading point. Then your next job is you need to have bus plan, how to assign the bus, come to pick up those people. Where the bus come from, you have to determine the route and stop too, okay? Here's the example of bus assignment model. Here's the bus as a routing assignment models. So based on the previous stage and pedestrians number and get to the bus stop. So here's the arriving bus stop information, okay? And this time, later on everybody get here, so it's reached the capacity, so no more arrivals, okay? And based on the information concurrently taking place in all the bus stop, you need to have what? Assign the bus come over here, okay? And then you need a bus route. Bus coming from where and go to where, okay? So you have to input where are the bus. D represent the depots, just some bus or school bus stationed there, okay, waiting there. After they drop all the school children's, they stay there, or some bus, if not en route, will stay in there. So in this impact area, you identify how many bus immediately can use. And of course, you want to use bus close to the impact zone first, okay? If not sufficient, you have to bus come from other bus depots too. And here the bus route. Everybody already know those bus route. So that is the information easy to be used by the evacuees. Okay, in bus depot, we got to know how many buses are available in those bus depot, okay? Again, this number can be changed, okay? For example, you're doing the vacation for the weekend, and this number will be different from the weekdays, okay? And then you input bus destination, where if you have a new bus destinations, okay, means you have to drop bus. A bus has to drop people at which locations. This could be a shelter place or could be subway stations. For example, some short distance evacuation, you try to send the people to the university or high school to put those people there temporarily before they identify need to have a further evacuation. Otherwise, the intermediate state evacuation could be a school, high school, okay, some area. So identify those destinations for bus to drop people there, and the bus can come back to pick up those waiting evacuees. And so here show you an example. Here's bus depot and a bus destination, okay? I show you, here's impact zone, and this bus route, destination here, okay? And some is, this area connect to a light rail, I believe, okay? Some light rail location. If bus drop people in the light rail location or bus drop people at the subway station, will be much easier to have a mass evacuation, okay? I see this all are the bus destination too, okay? And then you have to assign bus route. Here show you one example, each bus coming from the depot pick up pedestrians or evacuees from one particular station and then go back to safety destinations. the one bus route, and then he has to come back. Okay, you cannot just bus driver cannot escape. Okay, you have to come back to pick up another run too. Okay, you have to design the route. This time the route is here, and next time the route will come from what? Different destination too. Okay. So in actual operation, you have to consider very carefully every step in detail. Even you have considered every step in detail. In actual operation, still some uncertainty beyond your pre-plan. Okay. The previous one is one bus. This one is the same bus on the second OD run, different from the first one. Okay. Because they coming from here, coming from here and go out there, and second run from the destination, come back to to load some other pedestrians and come back again. So second runs. Here you show the same bus for the different runs. Okay. For all the buses, you have to produce the bus table for them. Here just show you one bus, previous bus, bus 246. We show them bus 246 based on the evacuation plan, coming from depot at time 0, and first have to come to this Royal Road to pick up. There are 16 people. Take 16 minutes, and drop off at some location. When come back to next pickup. So you have to design the entire bus route. And how does the information come from? Come from your mathematical models. Okay. So that's why I tell you, all you have to learn. I don't know who's teaching. I guess that's Joe or teaching the network design. Those are all useful. That's exactly every stop has some pedestrian, and they all experience some waiting time. You have to provide the first come first service, and provide a bus routing plan at different stop. Okay. All the available bus, you can use this same program to provide the evacuation. After all the evacuation, clear the pedestrian, then you can compute how long it takes. If you use the given number of buses, for example, take 45 minutes to clear the entire impact zone, and then you compare with your time window. If a time window show you only have 30 minutes to clear the evacuation zone, and with your current bus or transportation mode, you need 45 minutes. Then you know what? You know you have to prepare. You know you have to buy more bus and more plan to make sure something happens. You will have enough resources to evacuate those people. This is the most important function for these models as a pre-planning purpose. In actual evaluation, as I mentioned earlier, you still have to use a pre-planned scenario to evacuate. It may not have time to do the actual simulation operation. But this indeed will tell you what, where are the bottleneck area, whether given the current resources, current capacity of the network, current signal design, would that be sufficient if we have a major evacuation? Same as I mentioned yesterday, if those nuclear power plants are going to have a disaster, do we have enough car, enough service, enough routing plan to evacuate Taipei's population out of the impact zone within the certain time window? Otherwise, you all will be what? Most of them will be polluted by the nuclear radiation. Okay. If you do not have this plan, you have a plan, could still in problem. If you don't have a plan, then for sure you'll be in trouble. Okay. This one show you see. So all design have to be so detailed. Then you can see, just for that bus routing alone, can be a publication. The paper was just coming out from transit transportation journals. Talk about the design plan for the bus route. Okay, and every bus, available bus route, you first use those existing bus route because people are more familiar with those bus route. You may need to add some more buses too. Okay, if not sufficient, depending on your time window. Time window is long. For example, in the yesterday I mentioned about Ocean City hurricane evacuation. Usually you don't need a bus because hurricanes take a long time. You see a hurricane coming, usually you know 1 day ahead, right? You have a sufficient time for you to evacuate. You only need to intensify your message and give a different type of warning. Just intimidate people, say how strong the hurricane is going to be. and they all have their car. They can evacuate in this called pre-warning system, pre-planned evacuation. But in actual emergency or terrorist attack or earthquake or some of the evacuation, you don't know in a short time period. Okay, you only have a short time window. For example, a dirty bomb, if come in to attack, the window is very short. If the wind is strong, it could be even shorter. Okay, second round, third round. And I told you that's all student research. That's all my PhD student work. One major PhD, 2 master students, and 2 programmers work. Okay, and actually used now in Baltimore. And we have another online system. The one I mentioned to you about simulation, we also put it in online, so real time can apply. You want to know how many evacuees still at each bus stop, so you can. The bus routing plan has to be dynamically continue to change, right? Because bus stop people is getting less and less, and the plan has to be changed. So you also have to estimate based on the arriving pattern and departure pattern picked up by the buses to know how many remaining in each bus stop. Okay. And bus picker people, you don't want to create too much congestion level at the exit point. So at every exit point, imagine when you're beyond the exit point, there all will be vehicles, no pedestrians. Okay. So you check every exit point, bus volume, how many buses are waiting there. Okay, or going through there too. Partially you can know how many already evacuated and whether each exit point is overloaded or not. Okay, sometimes some particular route have too many people and overloaded and become congested. Other route could be available. You may want to evacuate people to that direction too. Remember, in the evacuation, we don't always evacuate to the area close to your home. Okay, your home may be in the eastbound. We could evacuate you to the southbound too. Because our model objective function is what? Minimize maximum throughput and minimize the clearance time. Okay, to clear the time of the impact zones. Okay, this exit points path. Okay, means the original one is what? Is a bus from some area pick up people inside the impact zones, and this is if the bus or passenger car evacuate to the control point, then you assign the path to those safe destination, this far away safe destination. Okay, so we have 2 level assignment paths. Once within the zone, so we pick up people. Okay, and then after pickup, you don't want them to get out anywhere. You want them to go through the control point and go to the safety area. Because in all the evacuation process, you want to make sure the entire evacuation is properly monitored by law enforcement. Because people sometimes go there, they have nothing. You have to provide the food, you have to provide all the possible supplies, okay? And they may not be able to come back in 1 week or a couple of days. Okay, you got to know how many go to where, okay? So you have to think about those issues in advance. We are lucky in Taiwan, we have never happened those major disasters in the past 20 years, but no guarantee it's never happened. Okay, and here's the distribution at the critical intersection. Okay, we want to know all those inside the evacuation at all the intersections. Where are the conditions, and do we have to do anything or not? Okay. Here, okay, those are critical intersections out of the evacuation zones, okay. And then you know the current prefer the distributions, coming flow and all the distributions, and see based on the distribution what are the conditions. I told you in the actual real-world large-scale system with uncertainties, our mathematical model can never reach actual optimization. Okay, all optimization provide a framework, but because the input data is uncertainty, your driver response uncertainty, and some information we may not have. Okay, so our mathematical model can never reach the optimum for those cases. So you always have to what? Use the feedback process to adjustify, to modify the control plan. Okay, but you cannot just do your own human intelligence without the mathematical model result as a background. Okay, otherwise it will be too far away from the ideal control conditions. So you may have to change the signal control as I mentioned earlier. So here's actual intersections. Okay, and here's the graphic intersection. And here every approach, each phase, what the signal timing, yellow time and red time you provide. Okay, so we have to, then do you realize in order for you to study the system, you also need the knowledge on what? On database issues. So if you talk about your a modern transportation engineer, as we talk about ITS researchers, you need to know a lot. You also need to know the database issues. You may not need to know how to do exactly by yourself, but you have to design the plan for that programmer to do it. Computer programmer cannot do the job because they don't know the system at all. They know how to program, so you will be the one direct them how to design. By the way, this programmer is from National Chiao University. I think he graduated, worked for the Gongyan for a couple of years and studied a double E in my university. And he come to work as a programmer for 2 years for this project. Okay, so you can see now after you all the plan and under operations, then you can start to check how good evacuation, okay, for the entire network. Not only inside the impact band, also this is entire network within the beltway, okay. And you see that moving the time frame to here, then you can see what happens. And it goes on, the evacuation continue at the congestion conditions. And here's the example of this control boundary, this beltway, okay? And here's 1, 2, 3, 4, 5, 6, 7 destinations, okay? That's predefined in all the metropolitan area. We define if something happens, where you can go. Those are mostly a suburban area out of the beltway. For example, in Taipei City could be Taoyuan somewhere will be a destination, or Linkou somewhere will be a destination, okay? I don't know, I haven't seen the Taipei's plan yet. But certainly you don't want the people to stay within the Taipei metropolitan area, okay? And this is so far, after evacuation, this distribution of the throughput means how many people arrived there, okay? You can see the number are different. Some area close, assigned quickly, but each area have their capacity too. Okay, you can see the throughput or arrival pattern of the vehicles or passengers or pedestrian evacuees during the process, okay? So they reach the maximum rate up to when? Per minute, okay? Okay, here give you the first case. And this is one of the most advanced, I would say, even in current transportation area, multimodal evacuation. The only part that we did not include is what? Subways, okay? Because unfortunately in Baltimore, we only have one subway and one light rail line. So we actually treat it as one bus line. So we send bus to there. But entire process, as you can see, cover what? You need the pedestrian models to assign pedestrians. You need a signal model to assign the signals. And then also you have a what? Two network integrations. Because pedestrian flow go into the parking area or go into the bus stop will become what? Become vehicle flow, right? Pedestrian become cars. Pedestrian become buses. And then you have a what? You have a next model, bus, routing model, to assign bus to those destinations to pick up the evacuees. But in the second level of the network, you do have two different types of vehicle. One, passenger car, they mostly from parking garage and go to your assigned control point. And second type is bus for evacuation. They pick up the pedestrians from the bus stop and then go to control point and go to the safe destination. But difference is bus will come back. So your traffic cannot be a complete one-way traffic. You have to maintain what? One route or one lane for bus to come back. But passenger car will just go out, will not come back, okay? So it's not complete one-way traffic. I hope you don't need to experience those scenarios, okay? But you have to prepare that. I keep mentioning nuclear power plant area. Every developed country, every cities close to the nuclear power plant, they do have this plan. They do have this plan. I don't think we have this plan in Taipei. We have a plan in the Jinshan, was close to the nuclear power plant. I don't think we have an entire metropolitan area. But if something happens, Taipei is within the impact zone. You check it right. Taipei is within the impact zone. Have to go beyond Taoyuan, then you can barely survive. And most people are going to come to Hsinchu, I suppose. Okay. This is another case study. It's a hard issue too. I mentioned about the active traffic management. Okay, this is a good example. Now we are in the process try to extend this project to include a run metering on the highway from Baltimore Airport to the I-95 commuting corridors. Okay, so this is one easy to understand, but also to show you what is active traffic management. The paper has been published somewhere. Now I have trouble to remember where are my papers, but you can find out from the keyword, variable speed controls. You see, that's all my student PowerPoint. That's one of my requirements. You got to have nice, good colors, okay? Don't give me a dumb color, black and white, okay? I always give them trouble to give me a black and white. One West VSL, you will see very commonly in the paper, okay? VSL and VSL combined with run metering together, okay? They call active traffic management. And we actually implemented totally 10 weeks, I believe, okay? And I show you the three parts, okay? What is a VSL, okay? Because we try to deal with congestions on highways, and there are many different approaches you can do. So one, of course, infrastructure renovation basically is we call supply side, extend the capacity, or you add one more lane, build another highway, build another elevated highway from Taipei to Taoyuan, now going to extend to Hsinchu perhaps, and later on they extend to Kaohsiung, okay, become another elevated highway. That's one of the approach, but very expensive approach, okay, or add one more lane. A second is from the demand side, urban planning we call smart growth, means you try to control, decentralize the population, all go to downtown to work, okay. You know, United States, most of the cities, poor people stay in the downtown area. And if you are rich people, you always try to go farther away. The one I show you Beltway, most rich people do not reside inside the Beltway. They're all farther away, okay? And that's causing a lot of problems, the peak hours, commuting problems. So now the more and more some cities think about decentralized way, tries to provide some incentive to have a small community which provide a remote office too. Okay, so a lot of high-tech companies start to move to the suburban area to have their own office place, a condo or apartment together, may have a shopping mall all together. Try to use a planning side approach to decentralize the demand to the major metropolitan area. Otherwise, this metropolitan will continue to grow and become a mega city. I gave a lecture on the mega city. You can see mega city becoming monsters and become a big problem to all the countries because more and more population move in the area and more congestion and more social equity problem too. And another way is what? Use a management approach to make sure you have fully utilized the existing capacity. because you look at the highway congestion, peak hour so congested, but after peak hour, I don't know the Taiwan's highway, but United States after or 495 is so congested, peak hours, almost like a parking lot. But after 10 a.m., 11, there's no, you can drive at the free flow speed, okay? So you think what a terrible investment. You spend so much money just for those 2 hours, 3 hours, okay? And some of the congestion during the 2-3 hours are likely due to bottlenecks. So that's why we have a VHOT, and VSO is one of the strategies, okay? VSO originally started from where? Start from the work zone area, and for this hazardous highway segment during the snow day. Let's say during the snow day, we advise you to change your speed to lower to be safe. In the work zone area, all study also start from the work zone. We publish quite a number of papers on the work zone control issue. You think about work zone, if you have a 3-lane highway, I always mention, you close 1 lane, then what happens? Suppose you have a 2 more lanes capacity, but in reality, you close 1 lane, you almost completely stop in the peak hour, right? You don't believe, go try tomorrow. Just on the highway, you stop your car on the highway, 1 lane during rush hour. Suppose you have a 2 lanes capacity, but in reality, completely stop. Why? People try to change lane, they run at a very high speed, and at that bottleneck point, they completely stop. And the capacity is underused. So you measure the output, you found out. The output flow is much less than the what? 2 lanes capacity, okay? So that shows you have not really used capacity properly. So this concept originally used for non-recurrent congestion, accident, or work zone. Then we thought about the same problem in the recurrent bottleneck also have a similar pattern. Means everybody try to weave in, sneak in the bottleneck area, and so causing the car driving very fast and suddenly stop, and then slowly moving, okay? So that's underutilized the capacity because of weaving or shockwave problem causing the bottleneck. So those kind of problem is the candidate location to apply the variable speed and then combine with run metering. The one example in Taiwan's freeway number 5, that's a long tunnel problem. That's it. I'm going to send the Taiwan a model, okay? Next year, my final lecture for Taiwan, and then we'll say goodbye to Taiwan. We're given a free N05 computer control model. They cannot produce it, but I don't believe I use my own student produce the control model, variable speed control, along with the run metering together for freeway number 5, the long tunnel, okay? This too will be my contribution, including Jianlun's signal model, my contribution to Taiwan, my final legacy. Then I'm not going to come back to Taiwan for any lecture, any presentation. Give up, okay? Anyway, and that is a suitable area for what? Speed measurement, speed control, include run metering. So in this one, we only use a travel time information system and VSL, okay? Later on, next time I come back, I will give you the combined operations along with the run metering. Okay, this show you why do we need a variable speed? What would be an advantage? You can see this is highway. This is from Baltimore Airport, okay? From Baltimore Airport all the way connect to the I-495. I-95 is a major corridor, okay? I-95, you know, from the from the Boston, all the way you can travel up to Miami. You may travel halfway, right? So if you want to enjoy driving and test how good your survival ability, you just start from New York all the way down to Miami, okay? I can experience 55-mile speed limit, 65 mile and 75, right? Up to 75, the later stage, okay? And that's East Coast, okay? So that's a major corridor. And show you if no control, in the typical condition, the speed originally coming from about 60, 65. And for a while, and then suddenly drop. You see, at the two interchange area, short distance dropped dramatically to the speed of almost 20. And after they didn't draw, after this point, come back to what? 50, okay? So there's obvious bottleneck in this area. There's two bottleneck area. Okay, weaving problem. That's why I mentioned we want to have a computer control. We'll put a run meter in those two locations. Why I want to do that? Because our governor is going to run for the president of the United States. So we want to do more high visibility project to show Maryland's transportation progress. Okay, then this is called VSA control. So this area is a suitable candidate because obvious bottleneck and go, but if they drop and continue to drop, then it may not be a candidate location for VSO. You may have to use what? Run meeting together, okay? But if come back, so clearly the capacity is sufficient. This area just because weaving, you know, weavings, people all keep changing lanes. And one changing lane causes another changing lanes, okay? So all results, just measurement can show you if do nothing or just provide travel time information, that's happen. But if you properly advise people to slow down the speed, by slowing down, they don't need to have a complete stop. In fact, could be what? Better travel condition, okay? So this one, if they use only a variable speed control, in this segment speed is drop, but not so dramatically. But we use a variable speed combined with the travel time information system to advise them, come with better result. And this result is can be better because that time we use the demonstration by university, so it's advisory. We just say advise them to take speed. It's not mandatory. Mandatory can be much better, okay? But you already can see with and without the proper control, here can go up to what? 30 miles per hour. The current condition only 20 miles per hour. And if with proper, you can compute the actual capacity there and the speed. So based on speed density relations, they could be proper control. If everybody follow you, could be around 40 miles per hour speed, okay? So you see a dramatic difference. Why do we provide travel times? Because we are doing an experiment period. We don't have the police power to mandatory ask everybody to drop down. So in the first case, we only we do the do nothing case to see what happened, collect data for 2 weeks. And second, we provide travel time for 2 weeks. And then we put the VSL alone for 2 weeks. And then we put the VSL plus travel time for 3 weeks, because 1 week was heavy snow days. And the reason with travel time is better is because you are advisory systems, and driver is kind of learning from the experience. The first week usually they don't follow you, but later on they found out day by day they start to cooperate with you, okay? And travel time is the way to convince them, hey, you follow my advice, you will have shorter travel time, okay? So we found out that travel time information is a way to persuade the driver to follow your advice. And that is very useful because the whole active travel management is try to get support, cooperation from the drivers, okay? I'll show you this information. Then you can see this area of reduction on the delay and the fuel consumption is a contribution of variable speed. Okay. In other words, from driver side, if you can work together, we can actually do nothing, reduce the stop and go condition. I think many of you have the experience. You drive at high speed, and then the bottleneck area you have to completely stop, and then wait for a while, and then slowly moving goes back. Okay, so why not? We just slow down, but you don't need complete stop. Same as a signal progression. Now you found out sometimes signal progression, you drive very high speed, but to reach intersection, you have to complete stop. But if we do a progression speed control, advise you proper speed, then your speed may not be as high as you want, but you don't need to stop at the intersection. Altogether, you still have a shorter travel time. So this segment is the one we try to maximize. Okay. And it's a benefit of the control without putting any investment on the infrastructures, okay? So how good your model can do is just see how much difference in this area. Okay. We're going to improve this part because this one's almost 4 years ago, completed demonstrations. But from research point of view, before I show the case, when you guys learn, you want to ask, okay? From the research point of view, one, how do I identify the control boundary for my VSO control, okay? Second, from research point of view, how many segments should I divide the entire control boundary? Because each segment you put a sensor, you put a variable message sign, so it divides them dynamically changes speed, okay? So come the issue, how many segments do you need? And that determines how many sensors do I need? How many variable speed sign do I need? Okay. Too many is not going to be work, okay? Too short may not be able to capture the dynamic variation. So the research point, optimal number of detector location and detector variable message sign is important both for model effective and also for operational cost. That's the one I need to estimate. And if you need a run metering, you can also estimate when will be a starting time for VSO control. If VSO control may not be completely efficient, then you want to when to also turn on the run metering. So overall advantages: reduce accident, increase speed, reduce fuel consumption. Okay, this reduce the delay. Reduce accident is one of the major concerns because in those recurrent congestion bottleneck area, if you have an accident record, you will find out usually have a lot of accident because traffic usually come high speed and stop. I'm talking about bottleneck, okay? If the entire highway is congested, it's different. Entire congestion, you cannot do variable speed control. It's not going to help. If the demand actually over the capacity, variable speed alone, it's not going to work because variable speed is trying to fully utilize a variable capacity. If the demand is over the capacity, then you have to use a run metering approach to control the entry flow. Because freeway or any roadway, you cannot have overcapacity condition, okay? Okay, just show you some example in different countries. I think some we see yesterday, this lane-based control, okay, is still variable speed control. And typically, this will have a static control, time of day control, or weather condition control for those locations. May have a spatial alignment or a little bit dangerous area, okay? But the one we're talking about is, so in European country, usually we call the segment-based control. They control entire freeway at different link, given a different speed and different lanes, okay? That's route-based VSO control. And now it's more popular in the United States. We talk about the bottleneck VSO control, slightly different. For example, if you apply in Taiwan's freeway N05 at the tunnel area, entry tunnel area, and the impact of the queue, that will be bottleneck control, VSO control. But during the Chinese New Year, that will be very congested for entire freeway. You want to what? Entire freeways, speed control and run meter control to ensure the entire freeway N05 always running at the capacity, okay, and at the speed maybe only 60 miles per hour, but we're not 90 and come with 20, okay. What you can do is make sure the freeway is always at the capacity at the proper speed. That's the best you can do, okay. The trouble is if you have a high speed at 90 for half of the freeway and another half is what, 20, 30 or stop, then it's a complete failure, okay? Look at our throughput will be below the capacity. So it's very popular in European countries a long time ago, but that time is still a time of day change. Maybe peak hours 90, 70 miles per hour, or peak 90 is time of day control. Now we're talking about the bottleneck control, applied concept combined with the link-based and the zone-based, work zone-based concept to the bottleneck control, okay? That's MD100. Welcome to Baltimore. If you come to Baltimore, you can see from Baltimore Airport, come out MD 100 to the downtown area. Two-lane highway, 50 mile per hour speed, change in geometry, same accident, okay? High dynamic demand during the peak hour. Volume surge at the merging area, rapid speed drop at the merging area. You can see this graphic. Come with 60, 55, and the short, almost 1 mile, 2 mile period, drop to 25 and come back to 40 miles per hour. In rush hour, 40 miles per hour is pretty good, okay? You don't complain. You can just travel condition. 40 miles equal to how many kilometers? 60, 70 around, right? It's good enough. And this shows you the control devices. Again, I mentioned many times, as academia and in the transportation area, you have to always think about potential application. You cannot say just publish paper, okay? Publish paper is our own job, it's our own lunch or breakfast, okay? It's nothing special, but convert to a product can be used by a practitioner is the most important for you to sustain your research, okay? And these are the from application point of view, those you need a camera there, we have detector there, VSL sign, message sign too, okay? You have message sign. If you want to do a VSL, you have to what? Pre-advise people, say speed control is coming, okay? I know Taiwan Freeway Bureau say, oh, we implement the VSL in the N05 tunnel, it's not working. Same as they always say, oh, we are doing a carpool, sharing never work. Of course, you use the wrong strategy, use the wrong way. Of course, not working, okay? You have to think about more thoroughly. Just a small experiment will show you what we have done, okay? You have all the sensor, speed display, and early advice, early warning message too, okay? Of course, this one is operated by university, so we don't have much budget to put all the necessary component. But next one we are doing ongoing now, I have a full, is an actual deployment, not just demonstrations. So what are the components for complete the entire systems? You have one control system for sure, right? In the control center, operate. One roadside display, and also website display. Website display for two purposes. One, the control is done by my lab. One, my lab can see the travel condition. You know, the real operation, you could do your own control at your office, but the roadside VMS may not display the information. Happen in the demonstration period, the connection between the message fall down, or then you found out you change your sign in the website, but the roadside still have the same message. So many of those problems could happen. So you want to make sure, and also freeway or highway agency, the on-site people, they can access to a website, they can also access roadside to make sure these two will have a, talking about the same control and operate at the same condition, okay? Otherwise, sometimes the connection problem, or you may not display the message properly. So we always need a website to share real-time information by all the involving parties. Okay, here's it. You see the first detector, okay? And we also use a license plate information devices to measure the actual travel time. I have travel time informations. You have speed message, travel time messages. Roadside display, you have speed limit, message, and estimate travel time to the drivers. Driver can see those information, okay? Message has two types of message. One is warning message, one is advisory of the speed messages. In the website, control side, that's our university research side. You have detected data, control area map, estimate travel time, and all those control limit information, and historical data. You continue to collect the data. Data is very expensive, especially in the United States, okay? Manpower is expensive. You guys cheap, so you can do a lot of manpower data survey. We are very expensive, not easy to collect data. I told you one student, one years graduate assistantship will cost $50,000, okay? Not 50,000, okay? One graduate student give RA, okay? In private university, even higher, okay? The public university, the overhead is your salary times 1.5. Private university usually times 1.8 or 9. So in the private university, usually one RA will cost professors $65,000 a year. It's how expensive, huh? So I don't send the student go out to collect data. Too expensive, okay? Okay, this is our operational period for no control, travel time control, VSL control, VSL and travel time display control. This system, now you can see that 1.1 mile, 0.7 mile, totally only have 1.98 miles. So speed from original 50 miles and drop to 20 miles in what? In 1.1 mile short distance, okay? Because they're weaving. And then they quickly go back to 40, and here around the 45 to 50 after passing US 1 to Route 95. So obviously, this is what? A bottleneck. Because the speed can go back higher, so indicate what? Indicate volume has not reached capacity yet, not over the capacity yet. The congestion is caused by not volume problem, by the driving behavior and weaving problem, okay? This actual data. You can see high speed, 50, 1.5 mile here, totally only what? 2.6 mile. Drop from 60 to 20 mile. 20 mile is considered stop and go condition, okay? So that's the reason it's a good candidate site for the variable speed control. And let's show the location, put the detector, each one have detector location. And this one is not necessary, but it's good to have some devices to measure the actual travel time for our model calibration purpose. But actual deployment, you don't need, okay? Because this is a research and display travel time information. See, we advise the speed to drop to 35. Here's 30, okay? If the actually speed could be higher, the reason from the data we found out, you tell them to 35, they will drive at what? 40, 45. So actually speed here we know could be what? Around 40. But we say advanced speed 30. I say 30, in the United States, speed limit of 50, we always drive at 60, okay? You give the buffer zone. Two reasons. One, police will not give a ticket within the 10 miles grace zone period. Second, detector errors have at least a 10 to 15%. So also you got to know the behavior response. Drivers always this way. Tell them 20, they will drive at 30. Tell them 55, they will drive at what? Additional 10 miles. So the actual control from the model computer should be, or remember, should be 40, then we put 30, okay? Then we do the actual measurement, the test is true. The actual speed is around 38, 36, okay? So that is a strategy. You have to play a game with the driver, unless it's a mandatory, means you have a camera there, okay? So reduce to 40. If they don't reduce to 40, you will give the ticket, okay? But unfortunately, in US, it's not easy to operate in this way. You cannot just randomly put a camera, say you want to capture the drivers. Have to pass by the government, by the legislators. So they cannot put a radar camera everywhere. So it's very difficult to put a mandatory. They consider you try to take advantage of the driving population to get more revenue, okay? And this is this control segment, okay? In this area, it's very clear, as you can see from here, very clear to see the control segment. But in some area, it may not so clear where will be your control boundary. Because here 60, 50, 25, 40, clearly you can see this will be your control boundary. But in some areas, it's not so clear, okay? So how to define the control boundary is an issue, okay? And you want to do a before and after study. Step, you want to make sure your data is reliable, before data is reliable. Otherwise, your before data is fluctuate day by day or different time period. How do I know after improvement is due to your system or due to the fluctuation of data. I saw some of the projects, found out that after have so much improvement, but before you only have 1 day data. So how could you know your improvement is actually system improvement or your demand change? So we have done several days data, make sure your before data has reached stability. Then you can claim your improvement is actually due to your system rather than the daily fluctuation. And based on the stability analysis, identify spatial and temporal impact, and then compare MOE and reach a conclusion, okay? This is before data, I can see up, drop here during this, during this time period, and then comes back. This daily pattern at 5 minutes, day 1. So day 2, day 3, day 4. So you can see the traffic flow pattern is very stable. So if stable, then you can claim any differences are due to your control operation, okay, rather than the random changes. You see another way is the speed before control. You see the 2 big drop here, right? Big drop, big drop. One's morning peak, one's evening peak. Very clear drop, and the remaining time stable. So if you say we are talking about expanded 1 segment, it does not justify the cost benefit, but just a short time period, and remaining time period, speed is still quite high. Okay, so we should try to control the measure first before you spend a lot of money, especially now most of the state countries is short of money to do a large scale investment, relatively stable, okay? So when you try to do a study, to satisfy your sponsor is one thing. For your scientific work is others. You have to make sure your model actually improve, not just try to mislead the people, okay? So all the 3 days, 4 days, the clear bottleneck time period, clear bottleneck patterns. So average volume of the no control and travel time display show this quite stable period. So we can indeed use the information to do a before and after study. See the average volume still all kind of stable, okay? And this no control and travel time display control, not much improvement on the bottleneck speed. But you can see just VSL control, they have some improvement. Origin drop below 35, but peak hour average speed can reach around 45. So you can see clear improvement, but still have the trends drop the speed, okay? And this one, if only in you put the VSL and travel time display, some improvement, but this some fluctuate here for that 1 day. But this evening peak have a quite obvious improvement, okay? Then you go more detail to see the, again, this system was not a completely optimized because this was a demonstration period. We want to make sure working first and collect data. And show the actual speed measured by small time intervals. This is the no control period from the upstream downstream, and this with VSL only, and this one with the best condition VSL and the travel information system. So the worst case differences between these two, 120 compared with the 32. Okay, certainly the actual condition not straight line, is fluctuate, okay? Small manner fluctuated. We simplify to show as a straight line. That time period or purpose try to demonstrate the potential of this area. You do a good job, this area will be increased. You do a poor job, will be the same as the current condition. But in terms of investment, it's very small. Think about investment. All you need to do is what? Just some detectors, variable message sign, if you control properly. Compare with expand 1 more lane. You know how much it costs, okay? You have maintenance costs, you have all the feature pavement costs, okay? And you see the more detailed analysis. The travel time you can see over the this peak hour period, there's this no control VSL travel time display only, okay? Not much different. But the one with the VSL and travel time does show the improvement, okay? Does show improvement. I mentioned to you, this system was not, the location of detector and the speed was not completely optimized. It was in the demonstration, try to show it working. We know it's working by some of the experience and simple models, demonstrate it's working. Then can be further improved with optimized control, dynamic change. But when you try to talk to a government agency, you don't want to show them too advanced because they have the trouble to believe and understand how to use. So you want to show the idea easy to understand by them and to implement first. And you see the average speed. The no control in the worst case can as low as 28, and travel time display a little bit higher. But in the best case, the worst case in the best case, 33 miles per hour. But overall, it's much more smooth compared with the previous case. Okay. And you also compare a longer time period, average travel time over different time period. Okay. 30 minutes, 1 hour, 1.5 hours. The congestion only lasts about 1 and 1.5 hours, so it's not a long peak hours. And this is differences you can see with different control segment, control strategy, and clearly show the improvement. Okay, I told you this even not at the condition of fully optimized control parameter and dynamic change, okay? Because we are not allowed to put a mandatory sign, just basic advisory. So when we use the data, first week of data is not much improvement. Because first week driver usually are not so sure, but drivers are learning. So the second week of data does have a much more improvement. So drivers can also work with you. I have heard a lot of people always say, oh, driver is not good and not willing to listen to you. That's not always true. No? If your design is good, makes sense, useful, driver is not bad guys. Driver, they want the good travel conditions, they will work with you. But if you have lousy design, of course they don't follow you, okay? You can see the differences, okay? The average travel time over the congested segment, over the control boundary, okay? And this measures the throughput, okay? And throughput, you will ask, why throughput has not much improvement? Because if you throughput, you measure throughput will be what? How many vehicles pass, okay? And this less congested period, or during the period, vehicles all pass. So you control the time period, then the same number of vehicles pass the intersection, pass the congested area. So not much improvement, okay? They're all about the same because in 1 hour period, the peak hour only 1.5 hours. So during that period, most vehicles pass. So you look at throughput all about the same, okay? It's actually improvements at the speed level, okay? So this improvement is minor. This is really not the improvement. This is actually about the same level of the traffic going over the same control period. Suppose the major number of vehicles pass, right? They all pass. The difference is some take longer time, some short time. So for example, you found that you put the 1.5 hours, this 4 will be the same, because given a long time period, they all will be the same. Okay. For example, you do the throughput without control for 1 segment over the control peak hour, because after peak hour, all the vehicles pass. So your measure throughput is the same. So if you want to measure throughput, you should use what? During that congested 5 minutes or 10 minutes or 15 minutes, how many vehicles pass? Then we show the differences, okay? Here, because the peak hour only 1 hour, a little bit more than 10 or 1 hour, 20 minutes. So under the control, most already passed the intersection. Here I show you the same difference you can see, okay? First 5 minutes, if you really want to see the impact of the condition, traffic condition, and the different strategy, you have to do a small time interval comparison. No control, you see the very beginning period, no differences, right? Okay, after 15 minutes, it's a congested period, and then start to show improvement. After half hour, after 1 hour, the condition continues to improve. And no control is not much improvement, okay, actually get worse, okay. So you can see in the beginning you start to implement variable speed, traffic flow will not immediately respond. Okay, and that's after a couple of days or a week. Otherwise, driver may not immediately follow you. So take some time for the traffic flow to back to follow your advisory. Okay, so you can compare this to no control and VSL control. Okay, in the beginning period, not much different. Okay, and after 15 minutes, start to show the differences. After 1 hour, quite a different impact. Okay, and these differences is a function of congestion level. If the bottleneck is very clear, the difference between the volume and the capacity is large, then this potential improvement will be large. Okay, if the difference between the capacity and actual demand is very small, then not much improvement you can do. Okay, because all you can do is to make sure the demand fully utilize capacity. So you have to make clear. Here just show you want to evaluate, you have to see small increment. Okay, they actually 5, 10, 15, you do the time dependent comparison. You can see when start to show the improvement. You also know what would be the learning period day by day, and also learning period from the control start to the control actually effective. So important to show the time dependent comparison. We just show you the category presentation here, not all. Okay, and then so what a system product? You have a system module, travel time estimation. That's a mathematical model, okay, not the cost. Travel time monitor system based on the detector information. Computation algorithm, that's no cost, just you know how to do. Advanced travel information system. This is not necessary, but a good supplemental system. As I mentioned, when you want the driver to slow down, you originally drive at 60 miles per hour. You want to advise them to reduce to 50. They will be reluctant unless they really know, oh, by reduce the speed, I will not be forced to completely stop. My travel time will not be reduced. So they are more likely to follow you. So those travel time information, at least in the beginning period, you should have those information to give drivers confidence on your operation. Okay, some of the research findings, smooth transition between the free flow and non-stop flow. That's most important. Okay, some state, now this is very popular, some state implement the system mainly for what? Reduce accident. Because come with the free flow speed and certainly drop to a very low speed, you know the shock wave will cause potential rear-end collisions. And that's one of the main problems. Okay, you can increase the average speed, reduce overall travel time, and reduce the potential incident, increase the total throughput during the peak commuting period. That means during the still in congestion period. Okay, if after congestion period, you measure the total throughput will be the same because just total number of people pass those areas. Certainly will be the not much difference. Addition via travel time control system, reduce potential accident, reduce the consumption, and reduce emissions. Okay, those are some of the reference, early reference. Now have a lot. Okay, a lot of those publications. You read the TRB papers. Okay, there's a second system. In this case, I mentioned earlier, when actually use if this difference not as high as you can do and the demand is high, you may couple with what? Run metering here, okay? That's what we're going to do. We found out this area, after 4 years, increased a lot of demand in the weaving flows. Okay, so you can put a dynamic run metering here to control the flow, but the run metering will not be activated unless the variable speed does not show the impact. Okay, so these two combined together is a very hot research issue. Okay, very hard issue. From recent 2 to 3 years, a lot of paper and almost all the major states try to implement the system because federal government give a lot of money to do this study. Okay, so if you got interest, pay attention on this issue. The issue here will be, I mentioned, how many detectors you need, how many segments you need, then how to set the speed control. You need some traffic flow model or not. Do you optimize the speed limit control for different segments at a different time period? That would be what? A complete dynamic control. And then followed by if you need a run metering, when do you turn on the run metering control? When do you turn off? And how to maintain the freeway speed and local arteria with so-called equity issue. You don't want speed on the freeway too high, and in the meantime have a long queue on the arteria. So there's equity issues. So a lot of study can do how to determine the run metering rate to support the VSL operations. Regardless you like or not, but you got to know the terminology, okay? What is VSL control? What is integrated control? Now they talk about VSL combined with the run metering. We'll finish the first one, okay? Second one we'll wait for tomorrow, because there's a big fire. Actually, a lot of fun. You work on those kind of projects, you know. You see your project actually demonstrate and see the good result. In the meantime, you can continue publish paper. It's some reward, okay? If you keep publish paper, I don't remember where your paper, okay? Now I don't remember where my paper. My student told me I have a paper last year. I don't know where. I don't pay attention. You got so many paper. Paper for what? Paper cannot be your lunch, cannot be your dinner, okay? So if paper is coming from your actual system application, then that's more meaningful, okay? You don't want to just do it, but maybe too early for you, okay? You don't want to do it just academic exercise, do a lot of paper, nobody pay attention, and never be useful, okay? May not be directly useful, but got to be useful. That is my suggestion, okay? And only your work is useful or potentially useful, then you can continue to receive your funding. Okay, I show you the one that's earlier than the Baltimore, the DC system. This is a different type of evacuation, the early stage. It's a corridor-based control rather than the network-based control. And part of the reasons I told you in DC is a special area. There's so many restricted zones controlled by CIA or those security agencies we cannot touch. You want people to go, they don't let you go, okay? So we change the model to a corridor-based model. CGIS is very useful. Now it become popular, so-called cloud-based system control, okay? I know some of you working on, but that will soon be replaced GIS and cloud altogether. It's a buzzword, but you have to follow the trend, okay? So the whole system, the feature, what is the DC-based system? This has been used by some company, become commercialized. I did not apply for any patent or any copyright, so they actually use without our acknowledgement. Okay, the purpose is create a corridor-based evacuation system. This is Washington, D.C. You can see there's a Potomac River, okay, beautiful Potomac River, and there's a D.C. downtown. And this side is Virginia, another side is Maryland. D.C. is cut one corner from Virginia, another corner from Maryland, become a D.C., okay? It's not a state. And the features enhance the network geometric feature for operational need. Use a satellite image and a field video survey combined together as our background data. It's MPO's Metropolitan Planning Office. Because DC, you have a cover three, almost like an independent jurisdiction. DC, Maryland, Baltimore. People from Maryland, DC, Virginia, Maryland, and DC. So traffic here could generate from internal DC resident or a lot from Maryland, a lot from Virginia too, okay? So if you want to deal with the traffic problem involving three jurisdictions, so you have a called metropolitan government work together, deal with the urban planning and traffic issues. For example, Taipei and Taipei County, the traffic come together, right? A lot of traffic coming from Taipei County come to Taipei City. And signal one side controlled by Taipei County, another side controlled by Taipei City. They don't work together, okay? I believe they're going to cause unnecessary congestion too, okay? Congestion level can be reduced if they work together as one system. Those kind of relations, you need a metro MPO to work on, okay? Major U.S. cities all have an MPO organization. Okay, similar to what we showed before, this is a corridor base, develop an impact area assessment modules and the corridor basis, okay? And this one is more fancy. They have a different type of impact. It's a customized output model for evacuation route as a route basis to get out of DC, because very few people live inside the DC. Only two types of people. One is very poor, one is very rich or embassy, they work for embassy or very rich people. A very small percentage are very rich people. Most are foreign government embassy people work there, okay? And most are poor people. So after evening peak hours, DC is no traffic. I don't suggest you go DC at the night too, okay? Not safe, okay? In customer network, select critical intersection, optimal signal timing plan. This is different from the previous designs. In the corridor-based evacuation, you don't want to have a signal control at every intersection, okay? Because have so many signal controls, then you have a problem to speed the evacuation. Also, you only allowed to have a turning movement at major intersection. Otherwise, you want them to just go out. But some key intersection allow them to do a turning movement, change directions, okay? And all other intersections will just all green. Let them continue go to speed up the evacuation process. And the system will also have a 3D animation. Now 3D has become a Mickey Mouse. Everybody wants a 3D, okay? You need a customized interface, okay? This is promotion packaging. The system MOE, signal timing plan, routing plan, demand routing, so it's all have a customized. So our purpose is to get the system done, and our sponsor can use directly. We don't need to have a training workshop. This D stands for DDOT, Washington DC's Department of Transportation. This entire systems structure, okay? Input modules, incident impact area, control flow options, okay? Your time windows, stage evacuation I mentioned yesterday. You may divide the all population into different batches, or the control room in a different area. You need a database evacuation network, evacuation demand, you need both, okay? Here I have a rule-based network decomposition. You want to decompose the network. One side for Virginia, one side go to Maryland, or based on your coming to your automation module for your control, and this output, your text output, your summary statistics, okay? You also have a map output too, okay? This basically is whole system structures. This is a case study. This actual, this Union Station. Union Station is the railroad station, okay? Long time ago, the railroad is still the main transportation mode, but still in the downtown area. You want to go to New York, you take a train here, okay? We don't have a high-speed rail in the United States, unfortunately, okay? So you take train or fly from airport. So this is the demonstration case study. They actually demonstrate and evaluate. This is the area have some dirty bond identified by security people, and then we immediately estimate. There are two issues you got to understand. In evacuation, if the impact area is within some control, you don't want to have a large-scale evacuation. You only evacuate those people within impact area. Otherwise, we are causing panic for the entire city. So in this case, we identify how wide the impact area are. You only control those routes necessary to evacuate those target population. You don't want make the entire city people unnecessary under the panic condition, okay? So that's called a control scale of evacuation. The previous one I showed you bottom is a full-scale evacuation. It's slightly different. Full-scale evacuation will be what? Network-wide evacuation. And this is small-scale evacuation will be a corridor-wide evacuation, okay? By corridor rather than by the entire city, okay? Here's the impact within the impact zone. There's a TAZ zone, all those zones covered in the impact area. we know the car, we know pedestrian, we know the vehicle demands, and those are the targeted demand we have to evacuate. And this certainly is a small area evacuation, okay? Okay, you can see from here, the zone, how many people in the zone, is just in the one that in the central downtown DC area, but it's a limit area, not the total demand only about 5,000 vehicles. Okay, this is the location here, and this Potomac River, okay? So here also have a model allow you to have a priority control, first priority, second priority, okay? Here's a corridor list, show you in this area, connect to how many corridors, okay? And this have a two-way you can do. One, model select how many will be sufficient. And I told you in DC area, there's some corridor you cannot use. Pennsylvania Avenue, they may not allow you to use, okay? So you have to eliminate some. They send you a message say this cannot be used, okay, for other purpose. And this is try to define the impact shape, okay? Depend on your emergency event and the nature of the emergency event. The dirty bomb or chemical will be different, and this will be given by the Homeland Security, okay? And here show you the operation process, okay? Here you also have some advanced functions or basic functions. Have instruction, define the impact area, okay? And then a model compute to evacuate the previous area. We only needed to use those 1, 2, 3, 4 corridor will be sufficient. If sufficient, then don't use too many, okay? Too many, you want to calm the resident. You don't want everybody to get panic and try to escape, okay? So that's based on the computation, those corridors will be sufficient to evacuate to Virginia and to Maryland area. And then you based on the evacuation time, that will be given by the Homeland Security agent. Tell you when you should evacuate, okay? And then the highlight you can see for your job is to determine how many people should go assigned to each route, each artery, okay? Or model main purpose, one, identify how many would be sufficient to evacuate the target population. Second, how many should assign to each route, okay? Third, how many, this dot point represents a control point. There are so many intersections, but how many should have a signal? The remaining intersection, you will turn off the signal, will let it all green to go, okay? Because this, I told you, is mostly is one direction flow. Ideally, you will have what? All green. But some intersections, because some people, for some of the response operation, you need a signal for them to turn left or turn right. But we only, by model, identify where are the locations allow for have a signal control and turning movement. That's also part of model's function. Okay, then you can see based on all the zone, you can see the demand here. Then you can run your system. As I told you, this model is hiding behind. Signal automation model. The first one is assignment model, assign evacuees to different corridor. Second, have a signal model to determine where are the critical locations. Third, determine the timing for those locations and different phases. The system MO you can see signal timing parameters, intersection turning fraction, only those critical intersection, demand routing, those are the output of the model. I can see each output have to be supported by what? Some mathematical model, which is our students' research, okay? Okay, then here's system output MOEs. This tell you at this time period, update time meter every 5 minutes, starting time, duration 5 hours, okay? And at different time period, when you start to do the system assignment evaluation, you can see up to now, 85 people out of the this number has been evacuated. Okay, system throughput. Okay, and this define what percentage has been evacuated. Okay, that's less than 15% has been evacuated. You still have a red dot. What is show the condition at each route volume. Okay, the route volume, corridor volume map during the evacuation process. You want to make sure if your allocation of the demand properly allocated at different route. Otherwise, one route could be very congested, another route could be light. Okay, here you can see one is already in the purple, then others still on the green. And here's try to identify among all those intersections. You can see from here, we only allow these three to be a control point. Police will be there, allow them to access and do a turning movement. All the other will be just outbound traffic to get out from DC. In this control operation, the safety destination for them is go to DC's Beltway. The next one I will present tomorrow is in the Beltway evacuation. Okay, because from DC government point of view, if you can escape, get to the Beltway, you are safe, and that job become what? Become Maryland's job, become Virginia's job. Okay, there's still a jurisdiction problem. They're only responsible to get rid of people to the Beltway area. And your model also have to provide cycle times for each critical intersection. So you know the green time for these directions, okay, green time, and those are no control, okay. No control means currently they have signals, but we just let them all green, okay. You cannot do the turning movement. See, ultimate control point means at the intersections, those key intersections, okay. You will have to design what percentage can let them go left and right, okay? And all the access point. Access point means what? From the impact area, get to the major corridor, okay? Those impact area still have some walking distance or some small segment for you to access. And whether they can access properly or not is also one of the issue, okay? So, for example, demand here, they can go to two different directions. Okay, which one you will guide them to go? That's have to based on the model, and sometimes to try and error to make sure you balance the condition on those routes. Okay. Okay, so we found out clear the traffic take about 55 minutes. Okay, for all vehicles to enter safe area, which is under the corridors, which is the some interchanges on the 495 Beltway, okay? And here you can see all our system throughput, okay? Up to 55 minutes, 100% already evacuated, okay? You take how long? 55 minutes. And this is a control time window. When we defined how long take to evacuate, it will be the clearance time. 55 minutes is the clearance time because we want to make sure everyone get out, okay? And here's a by route basis you can check. That's very important to check whether you balance. You remember your clearance times by all the people get out. So if one of the route overloaded, then your clearance time will be longer and could be a disaster. So you have a route by route performance throughput informations. Here's the distribution of the loaded volume. You see some is 19%, some 9%. See, Pennsylvania, they only give us 9%. I remember the bottleneck is there's some upper bound. We cannot assign too many traffic to go there, okay? Mostly goes to this route. Here's the vehicle enter the evacuation corridor, okay? It just means when they get out of the system. From 45 minutes, they all already get out of the system and take about 55 minutes to completely reach the destinations. And this is each DAZ. You want to make sure every control zone, how they evacuate. You can see the first one, the blue one is very quickly 100% evacuated. And the TAZ 67 take a longer time. Somehow the blocked by others here and get done. The yellow one take much longer, take about 45 minutes to have a complete evacuation. Because yellow one is between those zones. There could be a traffic block by other zones traffic too. But that's important to see, is there any zones left behind the evacuation process? Want to make sure all the people are safely evacuated. And this 3D demonstration, I don't want to show it, okay? Or the stump case. There's some advanced function for the whole system too. Imagine you can have stage evacuation, intersection control, link control, travel time estimation. In this case, originally we did not provide travel time case, okay? And later on we added some more functions. You can have a stage evacuation, even the some area can have first priority, second priority. Why? You try to approximate balance the travel time, balance the evacuation time for people at different zone. Okay, some first priority, they may take a longer route. Second priority may take a shorter route. Okay, so there's a different concern on how to finally reach a minimum level of clearance time. Okay, so your ultimate goal is your first priority, second priority, even the third priority is try to what? Smooth your demand to minimize the load to the traffic network. And the ultimate goal is try to minimum clearance time, okay? So how many priority level you should have is still based on your model, okay? Based on model to compute who, how will be in this priority list. So you add this function to the system and supported by another stage evacuation models. This has also been published, okay? And real operation, you always need a stage evacuation. In this case, it may not be necessary. This is a small area evacuation, okay? But DC is a very sensitive area. That's why we also offer the function for stage evacuation. And you also you can have a intersection control and the reverse lane operation. Okay, I think that's reverse. We have a reverse lane operation here. In DC's route are always small. Have a clear boundary, so you can do a reverse operation in the model too. But I mentioned earlier, this reverse operation have to be very carefully, because you just reverse one link could be create a bottleneck to a downstream, okay? For example, congestion at one link, you expand one more lane, induce more traffic, could be a problem for next link. So not every link can do the reverse lane operations. Have to be a multiple link together and relate to the actual demand distribution. Otherwise, you use a reverse operation, add lanes, could improve the current condition, but create a worse condition the downstream too. So this have to be pre-planned. Also could cause accident too if you do not plan properly, okay? People try to use the reverse lane and then back to the former lane. That transition process have to be designed properly, okay? And we also provide travel time information. And so you know, okay, you ask me to take which route, what will be my travel time? Am I be safe or not? Otherwise, everybody may try to run to the travel time they believe to be shorter, and the outcomes, the route with shorter travel time become a longer travel time, and become a bigger issue, okay? Estimate traffic condition and output, okay? And here to show you the route condition after what? After 2 hours has passed and what the traffic condition, okay? Okay, we're done here today.